program. This is Chapter 5, lessons by H.N. Holzman, Modern Residential Wiring, 9th edition. Lessons format adapted and narrated by H.B. Bayou. Conductors. Chapter 5. Some of the objectives. List the NEC rules regarding conductors for general wiring. Know the different materials used for conductors. Use the NEC to select a wire type when given a specific installation. Properly specify wire size using the American wire gauge or AWG or KC mills. Explain the cause of voltage drop. Compute voltage drop. List the factors that affect conductor ampacity rating. Determine the correct conductor size based on the circuit load using the NEC. Use the NEC to adjust conductor ampacity based on ambient temperature and number of conductors. Some of the technical terms: adjustment factor, American wire gauge or AWG, ampacity, circular mills, correction factor, derating, insulation, KC mill, marking, MCM, solid, stranded, voltage drop, and wire. Some of the definitions will be shown on the screen and not read. They are included in the text and in the reading. Code alert, Article 100, utilization of equipment. Utilization equipment utilizes electric energy for electronic, electromechanical, chemical, and heating, lighting, or similar purposes. Materials. The materials used in wire have great influence on the wire's ampacity, termination procedure, and environmental restrictions. These factors, along with cost and code limitations, have been taken into consideration when you're required to select the appropriate wire for a residential installation. The conductor must be able to transfer a current without generating an acceptable amount of heat. Resistance to corrosion is another factor that, if not accounted for, can lead to an eroded and unsafe conductor. The non-conductive component of the wire or the insulation is available in numerous materials. Selecting the right type of insulation may determine if the wiring is safe and long-lasting for the installation, or it's one that will cause problems for you and the homeowner. Conductor. Only copper and aluminum conductors are used in residential wiring. Both materials are flexible, affordable, and have a low resistance to current. Refer to Articles 300 through 310 in the National Electric Code, NEC, for general conductor information. Copper is the most common conductor material for electrical wiring. It is strong and resists oxidation or corrosion. Aluminum also has good conductance, however it is subject to problems as a result of oxidation and expansion. Proper preparation is critical to the connection's reliability. Before using aluminum, you must consult the NEC, any local codes, and the manufacturer's installation instructions. Questions about its use should also be directed to the local inspector. Local codes may have restrictions against its use. Insulation. Conductors that normally carry currents must have a non-conductive covering called insulation. Acceptable types of insulation are listed in Table 310.104a of the NEC, which was the figure just prior to this one. The most common insulation used in electrical wiring is plastic or rubber. These materials are excellent non-conductors or insulators of electricity. In addition, these insulated wires are often protected by substances such as braiding, jute, paper, more plastic, or metal. See figure 5-3. Type THHN is the most common wire used in dry installations, while THHW is frequently used in wet installations. The type of wire used depends upon the situation and environment where the wire is to be placed. Refer to Table 310.104a for detailed information regarding insulation properties. Again, that table 310.104a is in the NEC. Code alert, Article 100, dry location, a location not normally subject to dampness or wetness. A location classified as dry may be temporarily subject to dampness or wetness, as in the case of a building under construction. Damp location, a location protected from weather and not subject to saturation with water or other liquids, but subject to moderate degrees of moisture. Examples of such locations include the partially protected locations under canopies, marquees, and roofed porches. Examples of interior locations subject to moderate degrees of moisture include basements, barns, and cold storage warehouses. Wet location, an installation underground or in concrete slabs or masonry in direct contact with the earth in locations subject to saturation with water or other liquids, such as vehicle washing areas, and in unprotected locations exposed to weather. Conductor size. The size of the conductor to be used depends on the amount of electricity that it must be conducted, the length of the conductor, and the type of environment in which the conductor will be used. Our discussion of wire sizes is limited to copper wire. For aluminum, the wire size larger than that of copper is always required. Refer to the NEC to determine the correct size. Caution: proper wire size. Improperly sized wires can be very dangerous. If the wires are too small, they can heat up and destroy the insulation. This could start a fire or create a shock hazard. Figure 5-4 shows the diameters of copper wires that are typically used in residential wiring. There are two units of measure for designating the sizes of these wires. The first being the American wire gauge, or AWG. The smallest wire in residential wiring are 18 AWG to 1 AWG. The larger number, the smaller diameter. Or the larger the number, the smaller the diameter. After 1 AWG, the wires increase in size from 1/0, written as 1/0, again pronounced 1/0 AWG, to 4/0 AWG. Wires larger than 4/0 AWG are designated by the KC mil or 1000 C mils or circular mils. A circular mil or C mil is the area of a circle with a diameter of 0.001 inches. The reason that larger wires are specified in KC mils instead of diameter is because KC mil is a measurement of the wire's cross-sectional area. The area of the wire is important because it is a factor in determining the ampacity of the cable. Doubling the KC mil in a wire roughly doubles its cross-sectional area. History brief, 1000 to K or M. When wire sizes are expressed in 1000 circular mils, you may see the designation KC mils or MCM. Why is this? Before the metric system gained popularity, U.S. industry used Roman numerals to express multiples of 1000. Thus, if a factory wanted to order 5,000 screws, they would put 5M on the order sheet. Since M is the Roman numeral for 1000, if they needed 5 million screws, they might put 5mm. Cable sizes above 4/0 were designated in the same way. MCM stands for 1000 circular mils. So 500 MCM cable is 5000 circular mils. Using the metric system, this is expressed as 500 KC mils. Today, both systems of marking cable sizes are in use. Most branch circuit wires range from 14 to 10 AWG, with 12 AWG being the most common. You may have to use up to 4/0 cables for service entrance wiring. Residential work rarely requires cables larger than 4/0. Caution: stripping tools and stranded conductors. The overall diameter of a stranded conductor is larger than the diameter of the solid conductor of the same nominal size. Figure 5-7. Stripping tools that are designed for solid wire cannot be used on stranded wire because the tool will cut too deep and nick the conductor. Many stripping tools have two wire size markings for each notch. For example, a notch that is marked to strip a 14 AWG stranded wire is also marked to strip a 12 AWG solid wire. Selecting the proper wire size is important because it affects voltage drop and ampacity. Voltage drop along the wires may reduce the performance of the electrical equipment. Voltage drop. Voltage drop is the loss of electrical pressure or voltage along the length of a conductor caused by the resistance of the conductor. Resistance increases with longer wires, smaller diameter wires, and temperature increases of the wires. On installations of great length, the voltage drop may be so excessive that a larger diameter wire is needed to compensate. To compute voltage drop in a single phase 2 or 3 wire system, use the following equation as shown on the screen, where voltage drop equals to 2 times length times R or resistance times I or current, all divided by 1000. For example, the voltage drop of 50 foot of AWG coated copper conductors carrying 30 amps would be, as shown on your screen, where voltage drop equals 2 times length times resistance times current divided 1000, which is 2 times 50 in this case, times 1.6 or 1.26 times 30 divided by 1000, which is 3.78 volts, or approximately 3.1% of 120 volts. Remember, you want to keep your voltage drop under 3%. So 3.1% would be cutting it short, cutting it close. Thus, the actual voltage at the device is 120 volts minus 3.78 in this case, or roughly 116.22 volts. In this respect, not only the wire size or cross section is important, but the wire length is as well. Ampacity is the maximum current carrying capacity of a wire and its consequent heat dissipation ability. Table 310.15b16 lists the ampacity ratings of each standard wire. See figure 5-8. You can select a wire size table if the wire will be installed in the following conditions. No more than 3 current carrying conductors in a raceway or cable. The maximum ambient temperature is of 86 degrees Fahrenheit. The conductors with a rating of 0 through 2000 volts. To select the proper size conductor, you will have to know the type of conductor that will be used and the required amperage. You will also have to know how many current carrying conductors will be adjacent and the maximum ambient temperature. These last two requirements will be explained after this example. Selecting a conductor. Selecting a conductor size. A utility room in a home that you are wiring needs a 20 amp receptacle for the washer and dryer. The conduit will be run from the circuit breaker panel to a box in the utility room without going through the attic. The conduit will be the equipment ground and contain one current carrying conductor, hot, and one grounded conductor, or the neutral. All conductors will be PHHN copper. Because this situation meets the 3 criteria listed above, the conductor size can be picked from table 310.15b16. It appears that 14 AWG is ample, but there's an asterisk next to the 14 in the table. This asterisk directs you to section 240.4d, where it is stated that a 14 AWG conductor can be used in a circuit rated for a maximum of 15 amps. Thus, a 12 AWG conductor is needed in this utility room. See figure 5-9. Multiple conductor ampacity adjustment factors. The 3 conditions shown above table 310.15b16 are required because the ampacity rating of a conductor will decrease as the temperature of the conductor increases. Having multiple carrying conductors in one raceway or cable increases the temperature of those conductors. What if the conduit in the previous example contained a total of 7 current carrying conductors? Since there are more than 3 current carrying conductors in the conduit, an adjustment factor from table 310.15b3a has to be included in the calculation. See figure 5-10 as shown on your screen. An adjustment factor is a percentage that is used to reduce the ampacity of a conductor based on the number of current carrying conductors in a raceway or cable. This percentage is multiplied by the amperage determined in table 310.15b16. This adjusted ampacity of the conductor is the maximum allowed. If more amperage is required, a larger conductor will have to be used. For example, a run of conduit to a kitchen will contain 7 THHN current carrying conductors, 1 for a 50 amp oven and 6 for various 20 amp appliances and receptacles. According to table 310.15b16, the 50 amp conductor should be 8 AWG and the 20 amp conductor should be 12 AWG. Referencing Table 310.15b3a, the adjustment factor for 7 to 9 conductors is 70%. The 8 AWG conductor is rated for 55 amps. Multiply this by 0.70 and the conductor is derated to 38.5 amps. Derating is the reduction in ampacity after calculating adjustments and correction factors. The circuit requires 50 amps, and after multiplying by the adjustment factors, the AWG wire is too small. You can select each size above 8 AWG to calculate the ampacity to find an adequate conductor. In this example, the current carrying conductor for the range was the only one adjusted. The other current carrying conductors in the raceway should also be adjusted to ensure a safe system. Ambient temperature correction factors. The ambient temperature surrounding the conductors can also have an effect on the ampacity of the conductors. Table 310.15 B2A contains correction factors that change the ampacity of the conductors based on the ambient temperature. See Figure 5-11. If the conduit containing 7 current carrying conductors were routed through the attic of the home, a correction factor would have to be applied to find the proper wire size, depending on the home's location. Attics may reach temperatures of 120 degrees Fahrenheit or higher, far above the 86 degrees Fahrenheit that is allowed in Table 310.15b16. In the previous example, the current carrying conductor for a 50 amp oven was required to have an ampacity of 71.4 amps to handle the 70% adjustment factor. Since the conductors will now pass through an attic with an ambient temperature of 125 degrees Fahrenheit, the ampacity will have to be divided by a correction factor to figure the new requirement. Based on Table 310.15b2a, the correction factor is 0.76. The ampacity of 71.4 amps divided by the 0.76 correction factor to reach 93.9 amps according to Table 310.15b16. A 4 AWG conductor with a standard rating of 95 amps is required to deliver the 50 amps. Conductor Identification. The NEC requires that all electrical conductors be suitably identified. This is accomplished by having a proper markings and insulation coloring. These two methods ensure the correct wire type is used during the installation and that the conductor's purpose can be identified at any time. Marking. Marking is a series of letters, words, trademarks, and numbers that reveals key characteristics about a wire. The marking is usually printed on the outer insulation of the jacket of the wire or cable. If the surface is too small to be marked, the required information must appear on an attached tag, a reel, or the smallest unit carton. As shown in Figure 5-12, the required markings indicate voltage rating, maximum, insulation type indicated by a letter or letters designated by the code, the manufacturer's name, trademark, or other distinctive markings by which the organization responsible for the product can be readily identified, AWG size or circular mill area, Cables must also have markings that indicate number of conductors and outer finish or covering. Insulation color. Color coding of insulation on conductors is also used to identify wiring. See Fig 5-13. Although the NEC does not specify the colors of ungrounded conductors, the preferred colors are black, red, blue, and yellow. Code alert, Article 100. Grounded, connected to earth or some conducting body that serves in place of the earth. Grounded conductor, a system or circuit conductor that is intentionally grounded. Grounding electrode conductor, a conductor used to connect equipment or a grounded circuit of a wiring system to a grounding electrode or electrodes. And that concludes this chapter. Please review as needed. You can rewind, stop, pause, and also reference the text material. I highly encourage to look at the several tables, diagrams shown, especially the tables referenced from the NEC, which include tables tables 310.104a from the NEC. Also, you should review important tables from the NEC referring to this chapter, such as table 310.15b16, which used to be table 310.16, but it has changed. The number is now 310.15b16. And this table is the allowable ampacities of insulated conductors rated up to and including 2000 volts at 60 degrees C through 90 degrees C, which note that is 140 degrees Fahrenheit through 194 degrees Fahrenheit. And the name of the table continues: not more than 3 current carrying conductors in raceway, cable, or earth directly buried, based on ambient temperature of 30 degrees C, which is 86 degrees Fahrenheit. This is a very important table, 310.15b16. Please review it. Another table to reference this text and to reference this recording is table 240.4d. Another one is 310.15b3a. And another important table is table 220.12, general lighting loads by occupancy. Now to jump on the review questions. What are the 2 most common metals used in conductors? That would be copper and aluminum. Number 2, conductors that normally carry current must have a non-conductive covering called a jacket or insulation. Number 3, as the AWG number becomes smaller, the wire size becomes blank. It becomes larger in diameter. True or false? The notch on a wire stripper that is marked 14 AWG can be used on 14 AWG stranded wire and solid wire. And that would be false because the size for stranded and solid are different. The opening for the stranded is larger, 14 AWG, and the one for the solid it's smaller. So the one for 14 AWG solid equals to the 16 AWG stranded. Question 5. What is the loss of electrical pressure along the length of a conductor called? That is voltage drop. 6. True or false? Between two 12 AWG wires, voltage drop is greater on the longer wire. And that is true. The longer the wire, the more the voltage drop. And on your screen you can see a formula to determine your voltage drop. Determine the voltage drop of 100 foot of 12 AWG copper conductors carrying 20 amps. And the formula is shown. Voltage drop equals to 2 times length times resistance times current, all divided by 1,000. In this case we have 2 times, which is 2 times the 100 foot of length times the resistance of copper, of 12 AWG copper, which is 2.01, and that could be found in the NEC table 310. Excuse me, that could be found in NEC that could be found in the NEC table chapter 9, table 8 of chapter 9, where you have your wire characteristics. You can find the resistance for every 1,000 feet depending on the wire type, whether it be 12 AWG, 14 AWG, or 1/0 or 1 or 4/0 AWG. You can find the resistance and plug it in. In this case we have 2.01, and you multiply that by 20, which is your 20 amps. You multiply those and then divide it by 1,000, you get in this case 8.04 volts. Again, you find the resistance for the type of wire in the NEC chapter 9 table 8. Question 8. True or false? D rating is the reduction in ampacity after calculating adjustment and correction factors. That is true. 9. What size of UF or underground feeder wire is needed to feed a 100 amp service sub panel installed in a detached garage? Assume the garage temperature will reach 90 degrees Fahrenheit during the summer. Again, number 9, what size of UF wire or underground feeder wire is needed to feed a 100 amp service sub panel installed in a detached garage? Assume the garage temperature will reach 90 degrees Fahrenheit during the summer. For this, you multiply your required amperage, which is in this case 100, times your arrived at factor or ambient temperature correction factor. This is found in page 7-147 of the 2017 NEC on table 310.15b 2a, and you use in this case a 60 degree centigrade temperature rating conductor. And why do we use that? Because if you go to table 310.15b16, the UF table available for that, the copper cable is the first choice of 60 degrees C. So you go with the 60 degrees C rating cable, and you go to table 310.15.B2A. You go to the 60 degrees C temperature rating cable, and then you match it with your ambient temperature in Fahrenheit. In this case, it's 91 degrees. You get a range for your ambient temperature in Fahrenheit degrees from 87 degrees to 95 degrees. That falls, which 91 degrees fall inside of that range, and the temperature and the factor that matches that range is 0.91 from the 60 degrees C column temperature rating of the conductor. Again, you see that in table 310.15b2. You can follow along. You get your factor multiplied by 100. That gives you 91 amps, which, if you go back and look at table 310.15b16 once more, you see that the allowed ampere that falls under 91 amps, it would be your 95 amps, and it's going to be the number 2 AWG or 2 AWG wire could carry amperage up to 95 amps, from 85 to 95 amps, from 86, excuse me, to 95 amps. So that's the one you choose. That's the answer. Question 10. The markings of a series of letters, words, trademarks, and numbers that reveal key characteristics about a wire. That was a fill-in-the-blank question, and the answer was the marking. Know the code. What is the correction factor for a PHHN wire in conduit running through an attic with a maximum ambient temperature of 150 degrees C? Again, you go to table 310.15b2a to find that out. And we're looking for the first table you got to go to actually is the table 310.15b16. That's the first stop that you have to make to solve problems such as these. And you find your type of wire, which is PHHN in conduit running through an attic. So you look for your PHHN wire. We assume is going to be copper. So PHHN wires on your fourth column on that table, and that is a 90 degrees C rated wire, or 194 degrees Fahrenheit rated wire. That's not the factor now. It's just the rating of the conductor. And to find the factor, we basically use that rating, the temperature rating. That's what we get from this table first, which is the 90 degrees C. So we go to table now 310.15b2a, again on page 70-147 on the 2017 NEC, and you go to your fourth column, which is your temperature rating of conductor column of the one that says 90 degrees C, and the rating temperature range that we're looking at is, or the temperature setting is 150 degrees. That's your ambient temperature. So we match the 90 degrees C wire type rating with 150 degrees Fahrenheit, and that is towards the bottom, and that gives us a factor, a correction factor of 0.58. You can follow along again in table 310.15b to A. So to get your amperage, the amount of amperage that the wire could carry, the type of wire required, you need to multiply your required amperage, your load amperage, times the 0.58, which is your ambient temperature correction factor. Next, node code question. What type of conductors are referred to in section 310.15b-7? The type of conductors, looking at the 2017 NEC here, the type of conductors they're talking about, or they show here in this table, looking at the wrong table here. And I believe there is a typo here in this text. I believe what they actually refer to in this question is 310.15b17, not 7, which is in your 2017 NEC 70-151, page number 70-151, table 310.15b17, which is for the old 310.17 table, and it's the name of the table is allowable ampacities of single insulated conductors rated up to and including 2000 volts in free air, based on ambient temperature of 30 degrees C or 80 degrees Fahrenheit. Again, this is a table that gives you different types of conductors, such as TW, UF, RHW, THHW, THW, THWN, etc. Copper and aluminum. It gives you the different sizes. It gives you the different ampacity for each size, the maximum allowable ampacity for each size. So this is the allowable ampacities of a single insulated conductor rated up to and including 2000 volts. So this is for a conductor that is going to be running or carrying the entire load on its own. It's not going to share the load with other conductors. It will just be one conductor for each leg, the hot, one for the hot, one for the neutral. And one of them is ungrounded, of course, one ungrounded conductor. Okay, so number Question 3 for Know the Code. Section 310.15b3c describes which locations? Okay, question 3 of the Know the Code, section 310.15b3c describes which locations? And it describes raceways and cables exposed to sunlight on rooftops. That is per the 2017 NEC. Question 4 lists 3 types of conductors as defined in Article 100. If you go to Article 100 of the NEC, on page 70-35 of the 2017 NEC, you have 3 types of conductors on the left side of the column. Conductor bare, a conductor having no covering or electrical insulation whatsoever. Conductor covered, a conductor encased within a material composition or thickness that is not recognized by this code as electrical insulation. And the conductor insulated, a conductor encased within a material composition and thickness that is recognized by this code as an electrical insulation. And that wraps up and ends this chapter. Congratulations. Hope to see you in the next chapter 6. Thank you very much.